One thing that I just want to ask about quickly before we move on, because it's interesting since so much of our audience is probably philosophically inclined and have listened to a lot of our other conversations about philosophy where we've compared philosophy of physics with physics, philosophers with physicists.
Mm-hmm.
Something that you stressed about both of their thinking was conceptual clarity. Even though they weren't in philosophy departments, is it conceptual clarity that you identify with philosophical thinking that has such an important role in the work of the best physicists?
Yeah, I mean, two things, and they're both things you learn in philosophy. One is to make clear conceptual distinctions, because you always have kind of nearby ideas that are different. And if you're not careful and you just kind of slop around between them, you get into a mess. And the other is, of course, the same. It's a slightly different thing, but sensitivity to what follows from what, right? Logical sensitivity to see, oh, yeah, this conclusion follows from these premises. No, that conclusion doesn't follow. There's some tacit premise in the argument that you're missing, right? So often, of course, what one needs to do is notice that from some stated premises, a certain conclusion that seems to follow doesn't really follow. The reason it seems to follow is that you're tacitly making yet another assumption. And sometimes you can dig that up and put it in front of your face and you say, wait a minute, but I maybe that's wrong, right? Maybe I'm making a mistake in my inference here. So I think both conceptual clarity and, if you will, logical clarity. But you can't do anything well without them. You certainly can't do anything well where the subject matter is complicated, because you'll just get into a mess. And yeah, I would say, and as with Newton, again, just read Newton's Scholium on space and time. He's doing what we would call conceptual clarification at a certain point. He says, look, when we talk about space, time, and motion, there are two things we talk about. There's common, he has three words for it, right? Common notion and so on, these ones that are tied to our experiences. Like when I say, I'm not moving relative to you, or I don't see any motion. That is relative motion, right? That what I see, the fact that you don't look to be moving to me right now is because we're not moving with respect to each other. Even though in some sense you might say we're both moving as the earth rotates and blah, 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 right? And Newton says, look, there's common time, common space, common motion, which are used in everyday life. And then there's absolute true in mathematical time, absolute true in mathematical space, absolute true in mathematical motion. That's what physics is about. You can't do physics in terms of the common notions. And he's very clear about that. And why in everyday life it's kind of okay to use the common notions. But if you're doing physics, you have to use the sharp mathematical notions. And he makes that distinction, and then he gives this argument about why you have to make the distinction and so on. That you couldn't create Newtonian mechanics without being that clear. Einstein was trying to get that clear about electromagnetic theory in 1905. He again, in thinking about atoms, he said, let's take it seriously, right? I mean, people could be instrumentalists and say, oh, we postulate there are atoms, but that doesn't really mean there are atoms. It just means if you calculate or do something. And Einstein said, well, what if there really are atoms? What would we see? And this is coming off of Boltzmann and a whole bunch of stuff. The atom it was still questionable whether matter had an atomic structure. And Einstein thinks it through and he says, well, if there really are atoms, that would explain Brownian motion. That would explain why when I look at a little mote of dust, it jiggles around, right, in this random looking way. Why? Because it's being hit by these invisible gas particles. And looking at the nature of the jiggles, I can figure out how many there are, right? I can actually figure out empirically, right? This is again, let's take that seriously and see what follows. Now, the thing that happens is Einstein, of course, wanted to have that kind of clarity about quantum theory once it got going, and he never got it. He was never satisfied with quantum theory because he didn't have what he thought to be a clear physical account of even what the theory was saying, what it was postulating. And the response to that, as we know, was shut up and calculate. I've given you, I'll tell you how to calculate and make the predictions. I mean, maybe this would help. You could imagine Einstein, I mean, we can play this little game. Einstein goes to his physics teacher with this electromagnetic problem. He says, look, physics teacher, if I hold the coil and move the magnet, I get this current. If I hold the magnet and move the coil, I get the same current. How do I, what's the difference? Why is it so different? That teacher could have said to young Einstein, Einstein, shut up and calculate, right?
Yeah.
Use Maxwell's equations. Yeah, you'll use them differently in the two cases. You'll get the right result both times. Shut up. Stop worrying about what's really going on. And then we would have never had relativity. We have it because he wouldn't shut up, because he was trying to think it through, trying to understand it. Yeah, I think that is absolutely the mark of great physics, is to try to get clear about really what you're postulating and how it works. And having some equations that you can grind numbers out of that happen to be correct in terms of their predictions, that's not what physics should be about. Physics should be about understanding, comprehension, intelligibility, things like that. And that requires conceptual clarity. It requires clarity in argumentation, all of the things that make for a good philosopher.